Principles of Operating Systems, Chapter 3. Process Scheduling. Process schedulers are system software programs for handling process scheduling, obviously. What they do is select which jobs can be submitted, will be submitted into the system to be eventually executed, and to decide which processes to execute at any time. There are three basic kinds of process schedulers: long-term schedulers, short-term schedulers, and medium-term schedulers. A short-term scheduler, CPU scheduler, selects a process from the waiting queue and allocates a processor to it so that it begins to execute. It is changing the status of the process from waiting status to running status. The main priority or objective for the short-term scheduler is to optimize system performance. Now, of course, they have to have some set of criteria defining how they want to measure system performance that they're optimizing. Long-term schedulers are called job schedulers. The long-term scheduler determines which program it would be admitted to the system for processing. It selects processes from the created queue and loads them into memory for execution and inserts them into waiting or blocked queue as would be appropriate, whether they need resources or can start immediately. Primary objective of the job scheduler is to balance the jobs in the system, to get the right proportion of I/O bound and compute bound processes. And it controls the degree of multi-programming, how many different processes are working in the system at once. For the degree of multi-programming to be stable, the average rate of process creation has to be equal to the average departure rate of processes. If they're coming in too fast, things will stop. If they're leaving too slow, they can run. You can get more in at once. On some systems, they might not have a long-term scheduler. Time-sharing operating systems no longer have long-term schedulers. On these systems, a process automatically changes from new to ready. Medium-term scheduling is part of the virtual memory process. Removing processes from memory and storing on secondary storage and returning them back to RAM as needed. Running processes can become suspended if they make I/O requests. Now, when a process is suspended, it cannot make progress toward completion. When it cannot make progress toward completion, it makes sense to remove the process from primary storage, move it to secondary storage, opening space for other processes that can make progress toward completion. This process of moving processes from primary to secondary storage is called swapping. The process that's transferred to secondary storage is swapped out or rolled out. The medium-term scheduler is the system that identifies which processes get swapped out and which get swapped back in. The memory management is the function responsible for managing the computer's primary memory. It keeps track of the status of each memory location, whether each memory location is allocated to some process or free for allocation to a new process. Memory management determines how memory is to be allocated among competing processes. It determines which process gets memory allocated to it, when the memory is allocated, how much memory is allocated, and which locations in memory get allocated to each process. When memory is to be allocated, when a process needs or requests memory, memory management determines which locations are to be assigned. It tracks when memory is freed, deallocated, and when it is, the memory management updates the status of those memory locations so they can be used by other processes. At its core, the memory manager has the job of allocating memory to jobs and processes that they'll need for executing, and the task of reclaiming memory whenever a process completes, finishes, or for some other reason releases memory. In any system, an application program has to be restricted to its own areas of memory. Even the simplest single-user system, in a batch system, the operating system code has to be protected from being overwritten by application processes. So memory allocation has to involve some form of control over what memory can be used by application processes. In multi-programming systems, decisions have to be made concerning where a program process is going to be loaded into memory, and once it's loaded, decisions have to be made on what memory areas it be allowed to access. Of course, the limitations have to be enforced. Otherwise, there wouldn't be limitations. A memory manager then has to check the validity of requests for memory space, and assuming it's legal, the manager has to allocate a section of RAM that is not currently in use. The manager then has to keep a table of what sections are allocated to what processes. This is further complicated by the fact that although distinct processes are normally restricted to non-overlapping sections of RAM, there are going to be situations where multiple processes need to reference the same locations. And it's the memory management system that has to keep track of the rights of reference for the different processes and enforce them. In a system that supports virtual memory and or cache memory, it's the memory manager that has to set up tables to keep track of which sections of memory are allocated to which processes, which blocks are associated with which cache blocks, which process pages have been swapped out to where in virtual memory, and in the event of a reference to something that has been swapped out, it has to issue the I/O system command to retrieve the virtual page with the location referenced. The I/O module is a system for exchanging data between processors and external I/O devices. There are several different kinds of I/O modules. The most common ones are programmed I/O, interrupt-driven I/O, and DMA I/O. With programmed I/O, that's the simplest technique for exchanging data between processor and external devices. The processor executes a process that takes direct control of the I/O operation. It issues a command to the device and then waits till the device is done with the operation. It checks back from time to time to see whether or when the operation finishes. Interrupt-driven I/O has a lot of features in common with programmed I/O, but with interrupt-driven I/O, the processor doesn't stop and wait for the I/O operation to complete. Instead, it will issue a command to the I/O device and then go on processing other tasks, executing other processes. When the I/O operation finishes, then the I/O device issues an interrupt, and the processor processes the interrupt. It pauses the operation, the ongoing operations, and takes care of the I/O interrupt. DMA I/O modules exchange data directly between the main memory and the I/O devices without direct involvement of the CPU. With DMA, we get faster data transfer rate because the CPU doesn't have to be involved. We have the specialized DMA controller. The CPU initiates the transfer. It sends the commands to the DMA controller. It identifies which device and which memory buffer is to be used. then the CPU goes on dealing with other processes, while the DMA controller controls the data transfer. When the transfer is complete, the controller issues an interrupt so that the CPU can deal with the data that has been transferred. DMA is a technique that's especially appropriate for situations where the CPU and the data transfer rates are significantly different. Also, when the CPU is needed for performing other work while waiting for the I/O data transfer, situations where there's a high degree of multi-programming. There are lots of hardware systems that make use of DMA data transfer. In particular, disk drive controllers, graphic cards, network cards, and sound cards. The DMA I/O is different from pure interrupt-driven I/O in that the interrupt-driven I/O, the CPU does the data transfer from the device controller to and from the RAM. With DMA, it's the DMA controller that does the data transfer into and out of primary storage. The I/O module is responsible for moving data between the computer and external devices. External devices generally have characteristics very different from those of internal computer memory. Different response rates, different word sizes. So some form of interface is required to transfer data between devices and computer memory. Computer programs that executing on the CPU have to have some way of interacting with the external devices. An I/O module, device manager, manages communication with peripheral devices. One of the things it has to do is translate between the memory characteristics, and it also has to balance supply and demand, data coming in, data going out. And it has to enforce the policies dictated by device characteristics, as well as keeping track and maintaining system load situations and enforce local system priorities. The primary functions and responsibilities of the module are control and timing, processor communication, device communication, data buffering, and finally, error detection. When data is transferred between RAM and the external environment, they generally use the same data buses that are used in the execution of normal programs. Of course, you can't be transferring data on the data bus from CPU operations at the same time as DMA operations. So the I/O control unit has to transfer data from RAM buffers to devices or from devices to buffers only at times when the processors are not moving data to or from locations in RAM. The processor communication involves command decoding, data, status reporting, and address recognition. The I/O module gets its commands from the processor. It is transmitted on the control bus. It identifies the commands and any parameters that accompany it. Data that's to be stored on an external device or to be retrieved from an external device will be exchanged between the I/O module and the processor using the data bus. The I/O module also reports on the state, whether it's ready, busy, or in error state, so that the processor and the process that is working with the I/O can determine whether and when to send or receive another unit of data. Now, the I/O module is very often, usually, going to control more than one external device. So the module has to have a unique address for each device with which it is interfacing. The I/O module interfaces with the external data storage devices and controls the communication with them. So the module has to be able to send commands to the devices to control them, determine the status of any device to determine whether it's ready to receive a given command and data, send or receive data to or from the device. Now, data transfer rates between main memory and external devices will usually be very different. Most external devices are, in fact, much slower than primary memory, although a few of them are, in fact, quite a bit faster. External devices also tend to send and receive data in standardized amounts. Some of them 1 byte at a time, some a page at a time, a sector at a time in the case of hard disks. And input sizes and output sizes don't necessarily match. The processor might, for example, be sending or creating data a byte at a time, but to be sent to the hard disk, it'll generally be transferred as a sector, often 512 bytes. The I/O module then has to receive the data and store the data until it has the proper amount and the unit that's going to be receiving the data is in fact ready to deal with it. I/O modules are also responsible for error detection. Errors do occur, and the module has to detect and identify the error and report it to the system so that the computing system can take appropriate action. Data transmission, data storage almost always has some kind of error detection strategy for identifying when the error might have occurred, and, if possible, what kind of an error it was. Errors do occur in the storage of data and in the transmission of data. Error detection strategies tend to involve parity bits, and in Chapter 8, we will be dealing with that at much greater length.